and then I think we can proceed. So,
yeah, so
David?
maybe I'll give some instructions as always. So if you don't want to interact, I mean, if you don't want to be recorded, please interact through the chat. And you can, of course, ask questions in the chat and maybe later also in the round of questions directly to Professor Tadmor. So, well, today I'm very pleased to introduce Eitan Tadmor. He is a distinguished professor at the University of Maryland. He was the inaugural director of the Center for Scientific Computation and Mathematical Modeling during 14 years. He got his PhD thesis in Tel Aviv University, and before Maryland, he also had positions at Caltech, Tel Aviv, and the UCLA. And he also held visiting positions in the universities of Michigan, Paris 6, Brown, ETH Zurich, and Curran Institute. So his research focuses on developing analytical and computational methods to study nonlinear PDEs with application to shock waves, kinetic transport, incompressible flows, image processing, and self-organized collective dynamics. He has published more than 150 research papers on this field, and he has served as principal investigator for several competitive research projects funded by the National Science Foundation in the US, like the well-known research network KINET from 2012 to 2021. So Professor Eitan Tadmor has been listed as one of the most cited researchers in mathematics by the Web of Science. And he has received several awards like the joint Peter and Ritchie Prize by these joints by the ETH Zurich and Science Society. And well, today he's going to talk about the emergent behavior of swarming dynamics. So please, whenever you want.
Thank you very much, David. And thank you, Juan, for the invitation and the organization of this BIOMAT, which I participated live in the past. So welcome everybody from this morning in Washington, DC. The garden is in front of me and the light is above me, so I'm very pale. So I will talk about emergent behavior and a little bit of new observation with this result. So this will be sort of a survey talk. And the beginning will be with this guy. For those of you who do not know, this is Craig Reynolds, who was in the 80s working in the animation studios in California. And he wanted to create a realistic simulation for flocking, flocking of birds. And he came with these rules of engagements, which is referred to here as a tree zone model, where in concentric, three concentric overlapping regions, there are three rules of repulsion of, I will call them agents, alignment, and attraction. So this is basically is described here, and I want to emphasize that repulsion, for example, the agents, the members in the crowd steer to avoid local crowding, alignment steer towards a local averaging heading, and attraction steers towards local averaging position. I emphasize here the word local, which will resurface later on, but these are the three rules of engagement. Repulsion and attraction, since these are more familiar than particle dynamics, I will focus at the beginning on the key new feature, which is alignment. So I will talk about alignment dynamics. This is the reference, the 1987 paper of Craig Reynolds. So as a prototype model for alignment, this brings me to the Cooker-Smale model from 2007. We look at a collection or a crowd of n agents with position xi and velocity v sub I. And the dynamics is being told in this description, where the rate of change of the velocities of a given agent is balanced by a weighted average of the local gradients or the differences between the velocity of the agent we are talking about and its neighbors with velocities vj, and here are the weights phi ij, which are function of time. And given prescribed data, we run these dynamics for a large time, and we try to understand what is the large time behavior for this model. I will focus basically either on torus or Rn, basically no boundaries, because there is very little understanding of what's going on in boundaries, even though this is a very important aspect of collective dynamics. So what is being told here in this rule of engagement for alignment is that there is pairwise interactions which steer towards averaging heading. And this is indeed a key ingredient in self-organization, alignment that is, that appears in ecology, not just flocking of birds, but swarming of bacteria and insects, all sort of different scales in biology, interaction or dynamics, even cells, human interactions, and sensor-based networks. So I will not spend much time now in describing the spectrum of different problems where alignment plays a key role. But I would emphasize that these weights plays a very important role in this alignment. And these weights, which are function of time, and these are the weights for the interaction or the protocol for interaction between agents I and J, they are assumed to be a function which depends on the two positions. I will normalize this function. I will call it a communication kernel. And the assumption is that this communication kernel is non-negative. It's either positive or zero, meaning that there is no communication. So this will be in the background, the right normalization. This is the communication kernel. And the choice of the kernel is context dependent. There is no precise recipe for deriving this communication kernel. So let me mention few sources where these communication kernels come from. One aspect is phenomenological. For instance, we take the phi, the communication kernel, depending on two position x and x prime, to be a decreasing function of the distance between x and x prime. And this goes back to the original work of Cook-Smale, reflecting the fact that the communication, the strength of the communication decays as the distance increases. And here we have a Pareto-like decay of order gamma. Another source for deriving this communication kernel is empirical. Either empirical, which is very important, I don't have time to cover that, or is learned from the data, and here's just one reference out of many. And I have to apologize, I have to omit too many references. It's impossible in this kind of server lecture to cover everything. And then another source of derivation of this kernel, which is particularly close to my heart, is derivation from what I would call higher principles. Here's an example for such higher principle. There are others. And this is a reference to a recent work of with Ru and Shu, which appears very recently in Ait Arma. And the higher principle is the principle of anticipation. The idea is that when we look at agents in this context that I'm talking about are not particles. And one of the most important things for these agents is that they have either senses or sensors with which they realize the reality, and therefore we have to take into account that they react not to the current situation but to the anticipated situation, which is being told here. So we have a small parameter tau. This is the anticipated position, and at a given time t we change the rate of change of the velocities for a typical agent is given by the gradient of some potential. But the potential is calculated in terms of the metric distance between the two positions, the position of agent I and the neighboring position of agent J. But these are anticipated positions because we have to take into account that we can contemplate or anticipate what will be the anticipated position. If we expand in small tau these terms, we see that at tau equal to 0, we get the usual n-body problem. And for tau positive, we get an additional term, which is written here. So this is the second term. So we get now two terms. This is essentially the usual n-body problem. And it is the second term, that when tau is positive, the anticipation, which is the source of the alignment terms. And let's see what they are. So we have here two terms, the repulsion and attraction, that I will ignore for the time being. And I would like to focus on the fact that anticipation breeds alignment. This is the second term. And now we have these phi ij, which are the Hessian of our underlying potential. So these are either the Hessian or the approximate Hessian. So these are matrix kernels. And here we have repulsion and attraction depending whether a U prime which is defined in this fashion, is attractive or increasing or decreasing. So again, I put aside the repulsion and attraction for the time being. I want to zoom in on this issue of alignment. And here's a derivation in systematic way of the Cocker-Smale. In fact, the specific case that the phi ij are scalar, this is the Cocker-Smale, but this is derived from, the Cocker-Smale now is derived from a higher principle, and I will come back to this general framework, which is much more systematic than just phenomenological derivation of the Cocker-Smale. So we are back in the three-zone protocol, and we are talking about the role of alignments. And I remind you that it started. I started the talk with Craig Reynolds, who were seeking realistic description of flocking of what he called boids. I think the best way to describe it is, and this is important. I tried it just before. Unfortunately, I'm sorry. Let me try it again. It's this simulation, for those who have not seen it, is too important to ignore it. So let me try it again. Let me try it again. I'm sorry. I don't know why this is. Why it doesn't do it, but I will try my best. I believe that now you see everything, correct?
Yeah. Yes, we do.
You see?
Yes.
Okay, let me try now to see if it will break this time. So this is a simulation which takes into account this bird-like object, the boids. It's from the YouTube, so I don't know whom to credit it to, and it takes into account both the repulsion, the attraction, and most important is the alignment. And the alignment is giving you exactly this feature, which is really reasonably realistic. You can see that there is no impinging and there is no dispersion. There is sort of tendency to get together. And in a minute, now the alignment is turned off, and you can see that with the repulsion and attraction, you clearly do not see a collective behavior. You see just a dynamics which involves repulsion and attraction of particles with no special ordering. So the alignment is one of the key features which is responsible for the emergence of higher order structure that we have seen before, and now this higher order structure, which we have to somehow quantify, disappear. And indeed, if we wait a little bit longer, and then the alignment will be turned on, we will see that these structures re-emerge. And so this, in some sense, justify the statement that alignment is a key feature, even though its amplitude, measured by this small factor tau, is small, but for the large time behavior, it's important. And here the alignment is turned on, and you see what I'm talking about. Okay, so this was in order to convince that alignment is indeed a key feature. Craig Reynolds, just for the record, received for these simulations the 1998 Academy Oscar for technical recognition of this technical achievement for pioneering contribution. Nevertheless, to date, just 1 second. Because I cannot see now. Okay. Okay. Today, there is no mathematical theory, in particular to the local aspect of this three-zone model of Craig Reynolds, and this is the essence of this talk, what we know and what we do not know about the emergent behavior of this three-zone model. So what are the questions of interest? Several questions I will not be able to address in this running clock. One of them is, if you remember, the model begins with tau over n. And the statement is that the birds cannot count. So why do we scale it by n? And the answer is for convenience. It's just time scaling. It has nothing to do with the model. And a better scaling should be, for example, by a number which counts the total effect or the degree of these dynamics. But I'm not sure I will have time. It leads to multi-scaling and multi-flocking. This is a topic for a separate lecture. Another question which is of key importance is the different classes of symmetric interaction kernels, since we can derive them from in non-standard way. So what we can do is discuss different classes and how they affect the large time behavior. Let me mention a few classes. I already talked about interaction protocols, which depends on the metric distance. So these I will call metric kernels, and they go back to Cooker and Smale. And I already mentioned something which decays like a Pareto tail of order gamma, where this brackets indicates 1 plus r squared, square root of 1 plus r squared to simplify matters. Essentially, this is a behavior which is dictated in large distances. Another class of kernels are singular kernels. Here's a class of the risk kernels, where we take r to the minus gamma without these brackets. And in this case, we are interested both in the large time behavior and in the very small, not large space, large distance behavior, and then in the close neighborhoods. In this case of the singular kernels, agents which are very close are dominant over those which are very far. So we have this Pareto-like decay at far. We have the risk kernels. I should mention here short-range kernels. In both cases, these kernels have long tails. Short-range kernels, which appear in the celebrated model of Hicksteck, which I will not discuss either. One important feature here is these are metric kernels which have compact support. So the behavior is also very local. Another class of kernels are topological kernels. Here, a couple of examples. The idea is that we do not see just the distance between x and x prime, but we measure the crowdedness between 2 points in some control domain. I will refer to that later on. The topological kernel, I should have mentioned here, were actually motivated by actual, not simulation, but empirical data in a series of works from the beginning of the 2000s. So again, I don't make here the references, unfortunately. Anyhow, we have different classes of communication kernels, and I would like to share with you the key question that I would like to address, and here it is. How different classes of kernels affect the emergent behavior? Since I don't have any Maxwellian here that I can refer to, I would like to address the question how different classes affect the large time behavior and what are the major parameters in this question. What really make the different behavior depending on the communication kernel. I should mention that we will end this talk with a very concrete answer to this very diffused question. And finally, there is the role of repulsion attraction in addition to alignment, and this is still a separate lecture. Okay, so let me start now with the details for asking the large time behavior and the connectivity of graph dynamics. So this is the agent-based description. The phi ij, I remind you, is the communication kernel depending on communication function phi, depending on the two position. And I would like to interpret that as a dynamics on a graph. So we see the agent as those that create a graph with vertices which are the location of the agents, and the edges which exist if there is a communication between two agents positioned at vertices I and j. So we have here a weighted graph, weighted by this intensity of communication. And I would like to define now the energy fluctuation. So this is the L2 energy fluctuation. And the key point is the following statement. The rate of change of the energy fluctuation is identically given by the quantity which is written here. This is called the entropy. And this entropy is bounded from above by a quantity which is a scalar multiple minus scalar multiple of the same energy fluctuation. So let me clarify these steps 1 and step 2, because these are in the heart of matter. Step 1, this follows immediately by the antisymmetry of this term. The phi ij are assumed symmetric, and the term of the gradient here is antisymmetric. So when we multiply this by vi, we sum by parts, then we get this identity 1, which tells us the rate of change of the energy fluctuation is given by this entropy. And notice that the entropy is exactly the energy fluctuation weighted by the terms of the so-called adjacency matrix, the phi ij's. Now, if we can show that this term, the entropy, is upper bounded by a scalar multiple of the energy fluctuation, then we will be done by Granada inequality concluded that the energy fluctuation decay, and this will be the high road in order to get some sort of emergence behavior for the dynamics here as t tends to infinity. So in order to address this inequality too, I introduced the graph Laplacian. The graph Laplacian is defined here. It's essentially a matrix which takes in the off-diagonal terms minus phi ij, and the diagonal term is the sum of all the off-diagonal terms in each line. Notice that this graph Laplacian is positive and not negative in agreement with the standard notation in computer science. And with this formulation, we can write our dynamics simply as a heat kernel in terms of this weighted graph Laplacian. Notice that this is a Laplacian weighted by phi. And this heat kernel implies that the energy fluctuation is indeed less equal than the exponential, which we expect to have from Granada inequality. And now we found out this red term, a sharp quantity which quantifies this estimate, is given by the second eigenvalue of the weighted Laplacian. So let me repeat, we have the second inequality and we have a sharp second inequality, which is defined in terms of, so this is just an algebraic inequality given in terms of eta, eta being the second eigenvalue of this weighted Laplacian. Why the second eigenvalue? Because the first eigenvalue is 0, and the second eigenvalue is a quantity which is non-negative, 0 or positive. And we conclude that if this second eigenvalue is indeed positive, in the sense that it has a large enough tail which goes to infinity, then of course the energy fluctuation will go to 0. What does it mean that the second eigenvalue is positive enough in the sense of tail? It means that the graph is connected. In fact, this second eigenvalue, namely the spectral gap, is called the Fiedler number, and the Fiedler number is a known quantity which quantifies precisely if the graph is connected, namely that it's algebraically connected. The information propagates from every agent to every other agent. So not every two agents need to be connected, but every two agents directly connected, that is, but every two agents have to have interconnections through intermediaries. And if the graph is connected, in this sense, then the energy fluctuation will tend to 0, and if not, it will not. So this is a sharp condition which characterize the large time dynamics. And the problem that will cause me now to stop here is that this question of graph connectivity is unstable for a fixed n. Namely, even if we start with a connected graph at a t equal to 0, the graph may break down at a finite time, namely the spectral gap may reach 0, and therefore we cannot analyze this question because it's unstable for fixed n. To analyze the large time behavior, we therefore tend to large crowd dynamics. The dynamics of a large crowd tends to stabilize the behavior, the large time behavior. So this brings me to the large time dynamics and to the main topic of this lecture. I will consider the empirical distribution in the usual fashion, which is written here. It satisfies the Vlasov equation, and the Vlasov equation is driven, so this is the kinetic formulation, by the corresponding alignment term. So this is a quadratic term, again weighted by phi, and this quadratic term is familiar from the discrete description. If f is assumed to be the limit of fn, so there are certain assumptions here. There is a long series of contributions trying to justify, depending on the context, the passage from the agent base to this kinetic formulation. But what we get here is again this bilinear communication interaction. Here is the communication kernel. Here's the probability of staying with position x with velocity v, and the interaction with a bunch of other agents at position x prime with velocity v prime. We take into account all the other possibilities, we integrate, and this is the quadratic alignment term. Now, in order to pass to the large crowd dynamics that I'm looking for, I will capture the large crowd dynamics here in terms of the first two moments. That is the density and the momentum. And you notice that I really jump here because I really want to focus on the hydrodynamic description, which is derived through the kinetic formulation from the agent-based description. And this will be my large crowd dynamics. Okay. So here's the hydrodynamic description in terms of the density and the momentum. We have the usual mass equation and we have the momentum equation. And the momentum equation involves a pressure tensor and an alignment term. And let me now slow down. So first of all, the pressure. The pressure is a symmetric positive definite matrix P, which is given by the second moment of the underlying empirical distribution. So we run immediately into this issue of closure. And in order to understand the closure, of course, we have to understand what the dynamics is. And in order to understand what the dynamics, we have in some sense to know what the phi is. And the problem is that we have no closure. And therefore, this actually is not a hydrodynamic description. This is a mesoscopic description. It is exactly at this point that most of the literature assumes a monokinetic closure, namely it ignores the pressure and pays attention to the alignment, which I will discuss in a second. I would like to emphasize that all my talk will refer to arbitrary pressure without a closure. So there will be no closure. And here's the second term, the alignment term, and you are familiar with the alignment term. Here's our communication kernel. This is the macroscopic velocity. I'm staying at the position x. I have to take into account all the local gradients with all the other agents at position x prime. This is the local gradient weighted by my density and their densities, and I integrate over Rn. So this is the usual alignment term. So now we have here the usual dynamics, the momentum equation, the alignment term, and the pressure, which I did not close. So I want to emphasize again, the closure is left open. So this is not a purely hydrodynamic description. And at this point, I should refer to a very influential paper of, I highly recommend, of Vikshik and Zeferis, that they say that the source of energy making the motion possible are not relevant. So in fact, they did not insist. They claimed that the conservation of momentum, which is implied here, is not important. They are not relevant. And in some degree, I agree, and some degree I disagree. Namely, maybe the precise balance is not relevant. However, this means that we have a lack of thermal equilibrium. So we do not have closure in terms of equalities, but I will substitute by these equalities and non-equalities, namely the precise energy balance with inequalities. And I would like to convince you that nevertheless, the alignment is such a strong effect that for the large time behavior that I will be able to make to deduce substantial results. Okay. And I do this by looking at the decay of the energy fluctuations. Okay. So let's look at the decay of the energy fluctuation. So this is the energy, the usual energy involving the empirical distribution. And I decompose the energy according to the decomposition of the kinetic energy here, V squared, in terms of the macroscopic velocity, the fluctuation around the macroscopic velocity, and this term, which when I will integrate, will vanish by the assumption, the construction itself. So the total energy now will be decomposed into the kinetic energy and to the internal energy. Here is the usual kinetic energy, a purely macroscopic thing. And here are the internal energy, which of course involves microscopic fluctuations given here. There is still no closure. Now I look at the energy fluctuation. I define the energy fluctuation as the fluctuation of the macroscopic velocity. And I take here into account the symmetric addition of the internal fluctuation weighted by the densities. And just as we had in the discrete case, here is the following identity, which is very important. It's straightforward, but nevertheless it is important. we find out that the rate of change of the energy fluctuation is given by minus tau, the amplitude of, if you want the anticipation, it's the amplitude of the alignment. Here is the communication kernel, and here we have precisely the same terms that we have in the energy fluctuation. So this is precisely the entropy, just as we have in the discrete case. And now comes step 2, we are looking for an inequality, a sharp inequality, where this entropy is upper bounded by minus 2 tau times the scalar factor times the energy fluctuation. If we will have this inequality, we will proceed with Gronwell inequality just as we had before. The question is there such a tau, and what is it, depending on the communication kernel phi? So in order to do that, we will proceed with spectral analysis, which in fact, much of this work is summarized in a very recent article that I published in the notices. So it appeared last month in the notices of the AMS. And now, from now on, I will focus my attention on the torus. And again, the point is trying to upper bound this quantity in pulling out the phi in order to get this kind of estimate in terms of a sharp prefactor eta. So the first term, we see what happens here to the internal energies. In order to estimate the internal energy, and of course we have to estimate from below because there is a minus sign that appears there, I define the convolution, even though phi does not depend just on the difference of it's not a metric. I will define this kind of convolution, and I will denote by m the total mass of rho, which is constant in time, and it's easy to see that this is bounded by 1 over m times the mean of the convolution and the integral of e plus e prime. The reason for that is that the internal energy appears in this equation in additive form. And therefore, the only thing that we have to estimate is a minimal value of the convolution between phi and rho. This is pretty straightforward. Okay. Now we have to estimate the fluctuation of the hydrodynamic velocities. And to do this, I introduced the weighted Laplacian. So this is a Hilbert-Schmidt operator operating on a weighted L2 rho. And this is the weighted Laplacian that I introduced. This operator is the integration with this communication kernel, which is given in a precise form, the way it's written here, with the square root of the density. We should not care about the details here. They are very important, but this is the way I define the weighted Laplacian. And the reason I define this weighted Laplacian is the following. This L phi is a symmetric non-negative Laplacian. Indeed, if you see what its action is on a weighted function, namely W as a function, and I weighted it by the square root of the density, lo and behold, you get exactly the entropy. Namely, you get that this is the double integral of the communication function times the quadratic fluctuation of any function W, weighted, of course, with the densities, which is exactly what is needed, as you can see here, in hydrodynamic fluctuation. So, in fact, I tailored this weighted Laplacian that it will fit my problem. And this weighted Laplacian has a discrete spectrum with eigenvalues lambda 1, which is less equal than lambda 2. And from now on, you know the rest. Lambda 1 is indeed 0. This is the eigenfunction, which is a constant eigenfunction, weighted with the square root of the density as usual. So everything, it should be here less equal. Everything here hinges on the second eigenvalue, or the spectral gap. And we know that the spectral eigenvalue, by classical results, is characterized by the bilinear form associated with this Laplacian, with the normalized form here for all the functions which are orthonormal to the first eigenvector. And when you manipulate this term, you get precisely what we are looking for, namely, what is the ratio between the entropy and the energy fluctuation. And this is the infimum value of all w, such that the integral of all w equal to 0. And therefore, I conclude that we get a sharp, I emphasize that this is sharp lower bound, namely that this double integral is bounded from below by the integral of the energy of the velocity fluctuation. And outside, I pull the spectral gap of my weighted Laplacian normalized by the total mass. So this corresponds precisely to what we had in the discrete case. And here's the theorem. Suppose that rho and u and capital P is a strong solution of our problem with mesoscopic pressure. Then we have that the energy fluctuation decay exponentially. Well, the decay depends on the minimal value between the spectral gap and this phi convolution rho. We take the minimal value here and we have to integrate in time, and that's the statement. So now we have to study basically the spectral gap and of course, what is the meaning of this phi convolution rho? And this theorem applies for a general formulation. There is no closure for the pressure, and the kernel could be any symmetric kernel. So clearly now everything hinges in this theorem. So we are looking now for lower bound of this. This is the eta that we look at, which is the mean between these two quantities. Okay. So the first part of this, the discussion will be about long-range interaction. We look for lower bounds for the spectral gap. Here's the lower bound for the spectral gap. It's bounded from below by the total mass time the minimal value of phi, where phi is the minimal value of the communication kernel when we take into account all the positions in the support of the density. And this is very easy to derive. In fact, this is the standard estimate, and since this is sharp, this must be the lower bound. And of course, this phi convolution rho, if you pull out the minimum value of phi, you are left with the integral of rho, which I assume to be, I pull out the minimal value of phi, the integral of rho is m, and here's the lower bound. So in both cases, we get m times phi minus, and phi minus is the minimal value of the communication kernel. So the statement here is that we have to control the minimal value of the communication kernel. In particular, we require that the communication kernel will be global because we need this phi minus to be positive. Remember that we are talking about the local interaction according to Craig-Reynolds. Here we get the statement that if we have global communication, then we will get essentially that the fluctuation will tend to zero. Here is an example. Take the class of kernels with Pareto tails which decays of order minus gamma. Assume that the communication decays, then we have that the communication decays of order minus gamma depending on the diameter of the group, because the diameter is defined in this fashion. And then we conclude a classical result that if we have a density, velocity, and mesoscopic pressure, which is a strong solution, and if we have a long-range kernel, what does it mean, a long-range kernel? A long-range kernel means that this communication kernel is bounded from below by this d to the minus gamma, and if its gamma is not too large so that this will tend to zero, then of course the fluctuation will tend to zero and we get flocking. This involves long-range interactions because that's basically what is the statement here. And the prototype for this is a prototype for swarming behavior. For example, if the diameter not just stays constant but may grow, let's say of order beta, and beta times gamma is less than 1, then we conclude that the velocity fluctuation decayed to 0. And if the velocity fluctuation decays to 0, it means that the large time behavior they will approach the average velocity. I want to emphasize that this is an important statement because this does not take into account any behavior of the internal energy. The internal energy will also go to 0 without assuming anything about the pressure. So here are canonical example for long-range flocking from a lot of references. I do not mention them. So this is the statement that we have. We have a phi which is greater, decays like minus gamma. We assume a diameter which expands but not too fast. If beta gamma is less than 1, we get flocking. Here is an example. Assume that the velocity is uniformly bounded. If we assume that the velocity is uniformly bounded, the diameter grows at most linearly in time. That is beta equal to 1, and we conclude that there is flocking with this fractional power of the exponential if gamma is less than 1. And therefore, the diameter stays bounded. This is the case with the monokinetic closure. In the monokinetic closure, the system decouples into scalar equation. We have maximum principle for the velocity, the diameter stays bounded, and we get exponential flocking. So this, a large portion of the literature is a very special case because the velocity, we know how to control it. Okay. Here's an example which is less trivial. Let's take the case of matrix-valued kernels. In the case of matrix-valued kernels, and I remind you that these are the systems that we derive from anticipation. Now we do not have a maximum principle, so we have to be more careful. And indeed, in this paper, 2021, we show that if the matrix kernel satisfies this kind of Pareto, having a Pareto tail of order gamma, then the diameter of the flock may increase of order beta with this kind of restriction. So it may increase, but not too fast. And we conclude that there is flocking if gamma is less than 2/3. So there is a flocking in this case, even with matrix-valued kernels and not just scalar-valued kernels. And they are relevant in case of leadership and so forth and so on. I do not have time to cover that as well, since I see that I believe that I have a little bit few more minutes because I started late. Okay, so now we extend this discussion to anticipated dynamics. Anticipated dynamics, I remind you, is a dynamics, a hydrodynamics, is a hydrodynamics which we have here a mesoscopic pressure, which I do not dwell into. And on the right-hand side, we get the alignment, but the alignment is the one which is derived from anticipation. And that's what we get there. Notice that everything here is the anticipated position. When we do the bookkeeping for the anticipated energy fluctuation, when we conclude is that the energy fluctuation are given by the macroscopic, the oscillations of fluctuation of the velocity, and here is the additional term which comes from anticipation, and we get this very interesting statement which says that the rate of change of the energy fluctuation is given by the entropy. I mention it here because I always feel that there is more to it and I don't know what to do with it. Namely, in the anticipation model, we show that the entropy is given by the square of the material derivative of the velocity. We must be able to derive more than that. And we did certain conclusions, but I don't know what to do with that exactly. Anyhow, we concluded that in the case that we have attractive potentials, namely alignment plus attraction, in the case of attractive potentials, satisfying this kind of Pareto decay, we get that the anticipated support propagates, but not too fast. And we conclude that alignment plus concentration. So in this case, that we get attraction plus alignment coming from anticipation, we were able to prove that the large time behavior consists of alignment, all the velocities aligned in the same direction, and there is concentration in space. So this is another kind of behavior. And the surprising thing here that the potential need not be even convex. It should just satisfy these constraints. The reason I'm mentioning it here is that in order to indicate that there is a rich geometry of emerging structures with repulsive attractive potentials, much richer than just alignment by itself. So here I make a reference to Carrillo and co-workers because there is a long series of many works about the repulsion and attraction. So I push aside in particular the repulsion because we know very little about that, but it is extremely important to add it into the general three-zone models. So alignment and pairwise interactions, pairwise attraction. So if we take the pairwise attraction, I put it here as an external forcing, what we get there is in general that we converge to a traveling wave. And basically as I'm rushing a little bit, I wanted to show you one example when we have external potential. And in this case, it's a quadratic harmonic potentials, where the large time behavior is not just a linear traveling wave, but harmonic oscillators. And this is a simulation which will show you that it's more interesting. So you get here the crowd, and you can see the crowd concentrating both in velocities and in space. And this is zooming, what you see here on the right-hand side, around an harmonic oscillator. So you can see that you get potentially many more interesting structures that I do not have chance to discuss in this lecture. Okay. So far with regard to long-range interaction, which is very unsatisfactory because I would like to talk about short-range interaction. Namely, I would like to go back to this question of local. And of course, in order to do the local, there is a problem because I have to estimate, if you remember, I have to estimate this kind of entropy, and now I will limit myself to the case that I'm talking about metric kernels. So the phi will depend now on x minus x prime, and I'm trying to find the lower bound for this. There's a double integral here for the entropy, a lower bound in terms of the kernel phi. So what will be the lower bound for the entropy? We will handle the internal energy later on. So here's the here's the internal energy. Let's get rid of that. When we look at the convolution between the communication kernel and rho, I will bound it not by the minimal value of phi, but the minimal value of the density. The integral of phi is assumed to be 1, if you remember, that's the scaling. So now we have to assume something about the minimal value of the density, but nothing about the velocity, because nothing about the phi, the communication kernel, because it vanishes outside its compact support. Okay, so this is about the internal energy. What about the energy, the velocity fluctuations here? So here is a theorem. Suppose we consider a metric kernel. Let rho u and p be a strong solution of our mesoscopic problem, subject to non-vacuous density initially. So we have to focus now on the density. Then the statement is that the spectral gap, this is the quantity that I'm interested in, is bounded from below by a ratio which has to do with the minimal value of the density as well. Let me dwell a little bit about that. So this is the minimal value of the density. It is squared here. This is not homogeneous of degree 0 because of my own limitation. It should be homogeneous of degree 0. But this is the maximal value of the density. And this is a prefactor which has to do with the Fourier coefficients on the torus, the Fourier coefficients of the function phi. So this is a quantity which we can compute. And this gives us a lower bound on the spectral gap on the torus. And the reason for the importance for this theorem is that it enables us to check the large time behavior for short-range kernel in terms of the discrete Fourier coefficients of the phi, and assuming that the density stays away from vacuum. So this is an assumption because we need now this rho minus square. When we integrate in time, we want it, of course, to stay bounded away from 0 in the sense of a tail. So here's a corollary. As long as the max minus the mean, the variation of the density, is not too large relative to the normalized mass, then indeed this ratio has a lower bound and we get exponential flocking. So this is the first encounter with this issue of the density. So far we did not discuss the density, we discussed many other things. And from now on, we will see that the density is the major player in this result. In fact, in the case of one D dynamics, when we take phi to be a metric kernel, which is supported on the unit interval, this factor that I mentioned before turns out to be 0.1458, and we get this kind of exponential decay, where delta has to do with the fluctuation of the density. In the two-dimensional dynamics, the Fourier coefficients of the characteristic function of a ball has to do with Bessel function, J1, and we get another function, another exponential decay. The important thing is not only that we can compute it for arbitrary pressure, but the important thing is that I would like to zoom now on the behavior of the density. We have to stay bounded away. So this is the assumption here that we are staying bounded away from vacuum. So all these statements are independent of the size of the support of phi and the thermodynamics. Nothing about the thermodynamics, nothing about the support, but the assumption is that we stay non-vacuum. So indeed, the key issue is the non-vacuous behavior. And there is a general theorem which states that if the minimal value of the density is bounded by 1 over square root t, then we get flocking. And these statements, like we have here and like we have there, essentially tells us to be looking for connectivity in terms of the density. We need that the medium will be connected. There will be no hole so that the information will propagate just as in the discrete case. So that's the key essence of the large time behavior. And that's an open problem if we can quantify the behavior of the minimal value of the density. And I will try to convince you time and again that this quantity appears there, and this is the essence for the large time behavior for at least alignment dynamics. So let me move now to the second part of short-range interactions. And in this case, I will consider singular kernels. Single kernels, they look in the way they are written here. What I'm emphasizing here, this is a singular kernel. This is the dimension, and the singularity is of order alpha, so these are strongly singular. And the important thing is that we take kernels which are compactly supported. So you can see here that they are compactly supported, and here's a theorem for such singular kernels. If the minimal value of the density is bounded from below by the square root of t, then smooth solution minus flow. This is a general result. Again, the density, again staying away from vacuum, turns out to be the critical aspect. So we get unconditional, here we get unconditional flocking because the kernel is singular for short-range non-vacuous interactions. In fact, in the one-dimensional case, there is a result which says that you always get flocking with singular kernels, no ifs, it's just global result, but it's a very one-dimensional result. The bottom line, again, it is the support of the density, and we need the connectivity of the support of the density in order to enable propagation of information. Here's another example for the importance of the density, topological kernels. In the case of topological kernels, we measure the distance, not just the metric distance, but we measure the distance in terms of crowdedness, depending on the density. So here's a domain omega between the point x and the point y. Here is a domain omega x and y, and we measure the distance as the scaled total mass between these 2 points. And then now we think about a short-range protocol, which is a short range, as you can see here, multiplied by the topological distance. Why topological? Because it's inversely proportional to the crowdedness. And this has several empirical supports in work of pedestrian dynamics and so forth, and in particular, a series of works about the Starfleck project that I don't have time to elaborate. So we consider now this kind of topological kernel. You can see that it's considerably more complicated, but it's still symmetric kernel. And if it's symmetric kernel, then the argument before can be pursued, but now they have to be adapted. And this is a theorem which is taken, this is with Roman Schweitko, which says that smooth non-vacuous solution, if now the density is bounded by 1 over t, not 1 over square root t, then the dynamic should flock. So this is a much weaker condition than 1 over square root t. Again, the key issue, is it true? Is it true that the density is bounded from below? And we see now again the connection with propagation of information. Here's another example for short-range interaction, multi-species dynamics. So far I spoke only on the case that we have one species. In the case of multi-species, which are indexed by the index alpha, we have velocities and we have densities. And the idea is the species alpha interact with species beta. What distinguishes between one species and another? They have different protocol of communication. So now we do not have just one phi, we have phi alpha beta. So we have different species of communication, and therefore we have multi-species dynamics. And this is the one species, this is the multi-species dynamics, the agent base description. And where do these multi-species dynamics come from? They come from multi-flock dynamics. And again, I do not have time. They are derived in systematic manner from multi-flock dynamics, which is very important, but this is a topic for a separate lecture. So let me skip because there is not enough time to talk about multi-flocking. So let's talk about the multi-species. It is here, and here's a theorem. If we take this array of communication kernels, so this is a matrix of communication kernels. If this array is connected in the usual fashion that the Laplacian the spectral gap is positive, so we look here at the spectral gap of the weighted array of this communication kernel. If they are bounded from below in some Pareto tail like, then it follows that all the members of this, all the different species will approach the common average velocity. Why this is an intriguing result? because connectivity does not require all the phi alpha beta to be positive. Connectivity requires that sufficiently many will be non-negative, so there is a communication. In particular, the diagonal term, phi alpha alpha, need not be non-positive. So here's an example. Take a matrix, let's take the case of two species. Let's say species 1 interact with species 2, but not with its own kind. And species 2 interact with species 1, but not with its own kind. In this case, the large time behavior will be all of them eventually will approach the average velocity. And here is a 3x3 example, and so forth and so on. Okay, so once again, we see that in the short-range interaction, communication, the protocol for communication and to have connectivity plays a critical role. Now, of course, all these results reads the following. If we have a strong solution, then so and so. And the question is, what about the if? So when do we have global smooth solution? So let me conclude with few comments about the existence of strong smooth solution. If we have strong solution, then under certain condition of collectivity, then we get the large time behavior, which is flocking or consensus and so forth. So we are looking at this system. And of course, at this stage, now we'll have to say something about the pressure. There is a limit to how much I can proceed without saying something about the pressure. I just want to mention that at this stage, there are two mechanisms, competing mechanisms. There is a steepening of local fluctuation, which leads to finite time blow up, where the divergence tends to -infinity, and the alignment by itself, which tends to align all the velocities, and this, of course, prevents the formation of shock discontinuities, so the divergence of velocity stays bounded from below. Okay, so let me just mention few results that are known for the existence of a smooth solution, mostly in 1 and 2 dimension. So now I take the pressure to be 0. And there is alignment competing with the focusing, the steepening coming from the Eulerian part. So in the one-dimensional case, we get one-dimensional flocking hydrodynamics, and there is a global smooth solution if and only if the initial conditions, the initial velocity, its slope, is not too negative relative to the initial density. I mentioned this result, which is joined with Carrillo, Choi, and Chang-Wei-Ten, because it's if and only if. So we see here that there need to be a critical threshold, namely not all initial conditions give rise to global smooth solution, but a large class of initial conditions. In particular, we allow the initial slope to be negative, but not too negative. This is generalized in the case of fractional dissipation. In the case that you get singular kernels, so there's a series of works that generalize it independent of any initial threshold, and we get global smooth solution for alpha between 0 and 2. So these are a series of works of many people. In particular, I mentioned my work with Roman, and another approach by Do, Kiselev, Rizik, and Chang-Wei-Ten. It's a long story, again, a topic for a separate lecture. And the reason that it's a topic for a separate lecture is that if you compare it to the fractional burgers, namely you avoid the density here, then there is a finite time blow up when alpha is less than 1. Now, these results in the 1D were generalized to the 2-dimensional case, and in the 2-dimensional case, they involve the spectral gap of the symmetric part gradient of the velocity. And again, the statement is that the divergence of the initial velocity allowed to be negative, but not too negative, and the spectral gap initially should be bounded from above. So these are the 1- and 2-dimensional results, and that's where it stops. And the statement was, well, maybe when we go to the 3D, the problem is too complicated, but no, I would like to mention now here is another result, and that's really at the heart of matter in the last few minutes. So let me tell you what the motivation is. The motivation goes back to what I mentioned about Viksher. When we look at the internal energy, so now I revive the pressure and the internal energy. When you look at the dynamics of the internal energy satisfies this balance, which tells you that the time derivative of the weighted internal energy involves the heat flux, and this is the contribution of the alignment. So usually we do not look at that, but now we have the alignment, which is a very important term. And now comes the trace of the normalized pressure times the gradient of U. And here is a nice exercise which says the following. If you take the trace of the normalized pressure times the gradient of the velocity, it's always bounded from below by the minimal eigenvalue of the symmetric part, the symmetric gradient of the velocity. Here it is. This is a statement which is independent of the thermal equilibrium because it does not involve the pressure, the internal energy, or anything. So once this is true, what we conclude is that we should expect to have a threshold independent of the thermodynamics, because it means that this equation is converted into an inequality, and the inequality involves lambda mean of the symmetric gradient of the velocity plus the alignment term. This is exactly the quantity here. This is my eta, which I should put it in red if you want, and this controls the decays of the internal energy. And now, if we will be able to control the decay of the internal energy, it should lead us to large time behavior. Of course, there are many ifs here because I did not tell you what the pressure is. And in fact, the question is, is it true that once we have this inequality at the beginning, does it persist in time? It is true when the pressure is zero. When the pressure is different, then I do not know how to propagate this information in time. So what happens here is that this was verified in the 1 and 2 dimension, and this was the motivation for the following theorem. Consider the multi-D, any number of dimensions. There is no pressure because I don't know what to do with the pressure. Let's assume that initially we have a threshold condition which tells us that the minimal value of the eigenvalue of the symmetric gradient of the velocity plus the alignment term is bounded by a minimal threshold involving the density here. Then it stays positive, and this equation admits global smooth solution. So this is a general existence result, which is rather recent. And in the case of singular kernels, we can, of course, extend it both to topological independent of this threshold condition, but I will skip it here. Okay, I think at this point, I'm ready to conclude. I would like to thank you for the attention. And in the background, I will use this nice video. Thank you.
Thanks a lot, Eitan, for this Sarbi lecture, which was quite useful indeed. So now we can we have one clap here, and we can start some question rounds. If either you open your microphone and ask directly, or in case you cannot use your microphone, just write it down in the chat and we will read out for you. Well, maybe to begin with, yes, I can ask something about the first part of the lecture, which relates with the agent-based models.
Yes.
Where you had these results which rely on the full connectivity of the graph. I don't know if the terminology is the exact one, but the idea would be that somehow any two agents are connected by some path, so to speak.
Correct.
One would naively think that in case this is not true, somehow they would form subclusters and then evolve independently, and on each of those clusters, the whole story would repeat itself. But that would be a naive idea. Would that be true?
It's not naive idea at all. It's very precise. So you are absolutely correct. So there are two questions which are relevant here, which are rather difficult, I must say. And it goes like this. So this is the story here. If the question, everything is encoded in the time behavior of this, let's call it spectral gap, or the Fiedler number. Now, if the Fiedler number reaches zero at critical time, and then the multiplicity will decide exactly at that point how many clusters will emerge. Now, two things can happen. These clusters later on, but this, of course, is a completely different scale of behavior. This cluster can realigned altogether. But of course, this is exactly the multi-scale behavior. That's number one, aspect number one. Aspect number two, if you want to further study now all the different clusters, then it becomes really complicated because it's inherently unstable for a fixed n. And last comment, which I would like to make, because I'm working on this right now. This question, in some sense, the best I can describe it, I work on it quite a bit, and not just me and some of the people in the audience, so don't be offended. This question, this study is a little bit naive, and I think it was promoted a lot by enjoying the Cocker-Smell model. Let me tell you why this question is a bit naive, working on the discrete case as it is. If you are interested not in the cluster behavior, but just in the crowd behavior, at the very least, one has to assume that initially the crowd is connected. So I write it here in, well, it was never an issue, a really important issue, that of course lambda 2, namely the spectral gap of the initial configuration, is positive, but we never dwell into the connectivity of the initial crowd. The connectivity of initial crowd, large initial crowd, really has to do with topics like expanders. It's a much more detailed observation than just talking about the spectral gap. That's basically what I'm trying to say. And I started to look into that in a more precise way in recent times, from the point of view of dynamics of large graphs. And I would claim that it is a bit too naive to try to analyze the discrete model for a fixed n without dwelling really too much deeper into the graph structure, and just trying to do this Gronway-like estimate. The fact that you go to the large crowd behavior changes everything. But and once you talk about continuum of density, which is corresponding here to the discrete graph, of course, it changes because then you can do Fourier analysis and so forth. So working with a fixed n, just working as a discrete problem, is in some sense, I think, too naive. Or if you want to study, as you say, many clusters and stuff along these lines. Yeah, so this is the answer that I feel right now.
Okay. So far, we don't have anything on the chat.
So maybe myself, I have another question. So in most of most of the flocking results are, I mean, there's a strong hypothesis say that is we are assuming strong solutions, no?
Correct.
So how about flocking for non-strong solutions, like solutions that maybe have atoms? So in the
very good question. It brings, I think, and I know that several people try to do this. How about okay? So the question is, okay, let's okay. Let's take, for example, this alignment model, and let's forget about the external forcing, and there is not even pressure. So we know that it's not that a strong solution has to be interpreted in terms of momentum. It's not that a strong solution exists for all configuration, but only to subcritical configuration. So the question is, can one develop a theory for weak solution in this case? So can one develop a theory for weak solutions? So weak solutions for you can view it as a system of conservation laws, of course, but it's not precise because there is no pressure, so it's a very singular hyperbolic system. But on the other hand, you get the alignment term. And we know that the large time behavior of the alignment term is very fundamental. So there are several questions here. Or let me summarize it as follows. Can one study the large time behavior for weak solutions properly interpreted? I don't know. Now, whether weak solutions, you would like to take them in terms of Dirac or say measure value solution. I know that there are several works in this direction, but I do not know whether they study the large time behavior for, let's say, measure valued or dissipative. I'm not sure, maybe you know more than I do, but I know that the question is on the air, namely whether or not you can study the large time behavior due to alignment even after the finite time breakdown for a properly interpreted solution. Right. Mm-hmm. Yeah, that's absolutely correct, yes. I don't know. Open.
Okay, okay.
Open.
And maybe even for the kinetic, at the kinetic level, no?
Of course, of course.
Because, okay, here there's an additional difficulty that is, okay, this is a system of conservation laws, but at the kinetic level, you only have a PD, and still there are some, yeah, some difficulties, right?
So actually, maybe you know more than I mean, I did not dwell because I did not have time in such a lecture to say something about the kinetic formulation. So what is, I have to think what is the best result that I know. I mean, who has the best result about the large time behavior for the kinetic formulation? I'm sure that, I don't know, the group from Granada or Korea, or I don't know. I don't know what is the last word about that.
Well, as far as I know, most of the people just study any of the two levels, like discrete or macroscopic. But I know there are some results for the kinetic level. Maybe some ones by precisely by Carrillo and Fornacier, Toscani, and others, right? And even Jan Pestek, that you, of course, you know, he has some results at the kinetic level, right? For
that's correct, but there is
similar
existence or the large time behavior.
I think it's large time behavior, right? In a very specific case.
Yes.
But the full of the thing is not completely understood.
Yes, you're right. Yes, yes.
Yeah.
Right now, I cannot summarize. I have to see what are the precise assumptions, but somewhere between Carrillo and Pesek, you're right. And yeah, I mean, I did not dwell enough on the kinetic now because I was rushing. The question is, but they assume global kernels, right? If I remember
they are
global kernels. And I was trying to focus here. I wanted to get divorced from global kernels. It's tied too much to global kernels. And I thought I think it is important to understand the class of kernels which allow short-range communication, one way or the other. Yeah.
Okay.
Because when you have a global kernel and the kernel is singular, it's essentially fractional diffusion. Yeah.
Well, there are also weakly singular kernels where you don't have the collision avoidance effects, and of course you always expect measure value solutions and atoms, but still there something could be done. No?
That's correct. Yeah, that's correct. So for instance, I mean, basically, it's not what I'm trying to so the moral of the story is that I have to control two things: the velocity and the density. And when you come back to the kinetic formulation, so you will have to reflect on these two quantities, one way or the other. So the speed of propagation and the how you stay from vacuum. And I do not know how to compare now this. I mean, what is the result versus this? Because I wanted to emphasize here that you have to stay non-vacuous and to control the velocity.
Mm-hmm.
Okay, Eitan, I would like to ask another question.
I understand.
Yes, please, Juan. Go ahead.
A curiosity. I understand that when you take a matrix communication kernel,
yes,
then is the singularity is limited to 2/3, no?
Okay, so this is interesting that you mentioned. Okay, let me first of all zoom exactly where I wanted to. Give me just a second. Yeah, because this is not so. Yes, okay. So what really? Okay, so you can see here what's going on when you get the matrix-valued kernels.
Yeah.
This is fundamentally more complicated than Cooker-Smale. First of all, This is really fundamentally more complicated. It actually highlights, because we did so many, there are so many papers, right? So much in the literature about Kuka-Smale. And when you do this, the first issue that you come to cope with is, what about, how do you control the velocity? Because now it's a coupled system. The word is coupled system. So you have to control the velocity in order to control the diameter. You want to show that the crowd does not spread too fast. And in this case, we were able to show in this paper that the diameter may expand, but at most, not like t, but t to some power, beta, where beta is 2 over 2 to the minus gamma. So this could be larger than 1, but not too, I mean, we can quantify it. And then we need beta times gamma to be less than 1. So in this case, beta gamma less than 1, you get that gamma is less than 2/3. And when gamma is less than 2/3, so it does not bring us to the case of gamma less than 1, which we are familiar with, but the fractional power. Is this sharp? I'm not sure. Is this important? I'm very sure, because it tries to divorce from this usual thing of maximum principle for the velocity, and to show that even when you get a system, still there is a control for the velocities. Once you control the velocity, well, essentially you control. So this is by hyperellipticity argument. So there is a lot of, I mean, separate lecture is required, of course, but once you control the diameter of the group in this fashion, then you get flocking, and then once you get flocking, then the diameter stays bounded. So it's you can bootstrap this argument, which I did not indicate here, because I wanted to share with you what is going on under the hood. So for instance, what about existence for such system, I was asked. As much as I'm aware, no one did anything, and that would be rather interesting, because now we are not talking about scalar equations, we're talking about, if you want, hyperbolic systems, again, driven by a coupled alignment term. Yeah.
Okay, I understand. Thank you. Thank you also for the very, very interesting talk. I appreciate, and as you say at the beginning, okay, you are a friend of these Granada seminars from.
Yeah, so I mean, as much as it's very nice, let me tell you, if I have to make a choice, I always prefer to make it live either in Granada or in some other location for BIOMAT than in some talk from Washington, D.C. So
well, let's hope for the best.
Yeah. Anyhow, you deserve a lot of credit, you guys, for running this BIOMAT activities for several years. It's very nice.
Very kind. I wonder if there's anybody else that would like to ask something to Eitan. If not, if you allow for it, maybe just one final question on my part. Imagine that you want to get some numerical insight for those theoretical cases where you still have to work out the theory. For instance, this equation you have now in the screen, 2D, is the numerics already ripe enough to be helpful or not yet?
The numerics is always helpful, in particular when you want to get insight into several aspects. I mean, we have several numerical results, a numerical simulation that we did. We never reported that. For instance, if you add the attraction and repulsion, that's very important. I did not discuss this. It's actually not this theoretical open question, but understanding the behavior. Another aspect which is very important, there are many other, I would say, rules of communication for the phi that I do not elaborate here. And it's very easy to formulate the rule of communications. You run it into test and you get very interesting results, and proving that is very difficult.
No, but
yes, go ahead, Juan.
No,
Yes.
my point was that it is technically feasible to do it, that you can simulate that equation in a
Of
reliable fashion to get some insight, which is
course.
extremely nice. Okay, okay.
So, for example, even you take the matrix valued kernels. I mean, it's so rich because remember, it's any symmetric kernel depending on x and x prime. Well, which has this kind of Pareto-like decay metric lower bound. But still, take the simulation with topological interactions. It's fundamentally different than the metric interactions. I think that these theorems do not always capture the richness in the behavior that is hidden behind these models. And this is really realized only in numerical simulations. Only numerical simulations.
Lots of things indeed.
So I'll just give you a hint and then I will conclude. Even though I write this, you understand that all of these can be derived from this anticipation model. And in the anticipation model, for example, I showed the numerical simulation. You notice that the numerical simulations were very interesting. Not only that the velocity aligned, but also the position. They reach a consensus from the point of view of positions. It turns out that the anticipation dynamics has a fundamentally different behavior than the usual alignment. And we saw it in simulations. I will stop just here, just tell you, we are trying to prove it. So it's fundamentally different. Even though it seems the same, theoretically it's the same thing, you expand, no, it's fundamentally different from practical implementation when you simulate that. So not everything is just alignment or concentration. There is more to the dynamics that you have to do the simulation to get insight.
Great. Thanks a lot.
Thank you very much.
So let me conclude here that thanks a lot for accepting the invitation, for delivering the talk, for bearing us in the question round. Thank you everybody for attending the seminar as well. I will just briefly remind you that next week we will have Henry Berestiki, same day, same hour. Thanks a lot, everybody.
Bye-bye.
Thank you. Thank you.